so our next lesson is on multiplying algebraic expressions. And some of the topics you want to know from the past here, so again, you can go back and look these up or review them if you need to, or at least just think about that. Do I know this? Using the distributive property to multiply numbers, or maybe you already know a little bit about that with expressions. Exponent rules, especially like if you multiply two exponents with the same base, let's say, like x squared times x to the fifth, or even if those are numbers, that we add the exponents, and how to find the area of rectangles, okay? So that would be length times width, and anyway, yeah, so you can think about that, look that up if you need to. Let's go ahead and start with a warm-up. Anytime we talk about something algebraic, it's important, or we learn something new algebraically, it's important that we think about the number version of it first, because it turns out that algebra is actually, a lot of times we think of algebra as just like, oh, algebra is when you use variables, or when something's unknown or missing, and it's actually deeper than that. In fact, algebra is not really just about using variables. I saw a really cool thing recently, and this would be something that's probably helpful for you guys. Let's say that these two things I write here, A and B, are just like numbers, okay? Well, when you were in elementary school or younger, okay, so you learned what we like to call arithmetic, okay? And arithmetic is essentially just calculations. Okay, so that's what you started out. When you started learning about numbers, you learned calculations. We call that arithmetic. That was like your elementary. So this arrow represents a connection between these two numbers, A and B, right? So you learned all sorts of calculations you could do to two numbers or more. But now that we're, once you got older, and that would be like middle to high school, you start thinking algebraically when you're in middle school. Then you learn algebra, and algebra is much more than calculations. Algebra is about the relations between two numbers, okay? And we'll talk about this as we go through this lesson, but there's much more than just like, oh, can I do a calculation? Algebraic thinking is, are you flexible in understanding how to like break a number apart or work with a number in many ways, or like we sometimes want to do, find the missing piece in a calculation by thinking backwards, which is very algebraic. So let's go ahead and move on to our warm-up for today. I want you to, in your head please, okay, try to multiply these three pairs of numbers, okay? Find these three products. And then we'll come together and we'll look at the answers afterwards. And I want you to try to do these in your head in a way that's not like you do it on paper and pencil, where you like stack them up. I want you to try to do it in a different way, okay? So go ahead and pause right now, please, and do that in your head. Try to write down the answers for these, and then we'll check them together. Okay, so there's lots of ways to do this, and I'm not going to cover every single little way. But one of the ways that usually comes most natural to students, and I want you to think about right now, is 13 times 7. It's easy to think about the 13 as a 10 and a 3, because we can multiply 7 by 10 and by 3 individually, and that's pretty easy. So if you think of this as 10 plus 3 times 7, and then we use the distributive property, then we get 10 times 7 plus 3 times 7, which is 70 plus 21, which is 91. Okay? And maybe you did that a different way. We could have thought of 13, this is kind of weird, as 20 minus 7 and then times 7, right? Because the 13 is still the same as 20 minus 7, and that also wouldn't be super hard to do that way, okay? But for now, I'm going to use like the adding way, and probably we'll do something similar for each of these things. Well, let's do the next one. You may have also done this in the same way. There's lots of ways you could think about this. Maybe you already know that 4.5 times 2 is 9, and then you can add one more 4.5 onto 9 to get 13.5. That's a great way to think about it. If you did a similar way here and we use distribution, because again, that's our focus actually today, You might think of 4 as 4 plus 0.5 times 3, and then again distribute the 3. 4 times 3 plus 0.5 times 3 is 12 plus 1.5, and we still get the 13.5, same as we did there. Okay, so again, there's lots of ways, and this is what I talked about. This is where you're flexible with numbers and how to break them, pull them apart and stuff, and that is algebraic type thinking. And then this one, again, same deal. You might choose to do it in the same way. There's an interesting way I thought about for C, and I kind of have two ways. So again, if we did the same thing with distribution, which I'll say again is kind of our focus in this lesson, then we get 2 times 0.8 plus 0.4 times times 0.8. And then here you get 1.6. And then this is a little tricky because 0.4 times 0.8, we have to think about that decimal. Just remember, if I did, let's say, 4 times 0.8, that would be 3.2. 0.4 times 0.8 is 0.32. And then if we add those together, I think we get 1.992. So that would be our final product, okay? So we get those as our answers. One last thing to talk about for this, as I was going to mention, is I think this is a really cool way to think about it, especially since we've talked about decimals recently. 2.4 is 24 over 10, and 0.8 is 8 over 10, right? And multiplying fractions, I guess I could have put that in our prior knowledge, would make this become over 100, 24 times 8. And if I did 24 times 8 using the distribution thing, then what I would get is 20 plus 4 all times 8 over 100, and that would be equal to 160 plus 32, which is 192 over 100, and of course 192 divided by 100 is 1.92, like we got there. So a lot of times with decimals, it actually helps when you're doing the calculations, especially if you're doing it in your head, to maybe think of it as a fraction over 10 or over whatever power of 10. Okay, so again, make sure that you are okay with those things. That's a good warm-up to get ready for our actual lesson here with multiplying algebraic expressions. So let's move into doing some examples and learning some background from that. Okay, so let's look at another example to start out here. And this is another number example, right? So technically, so far, I'm asking you just calculations, right, arithmetic, but the algebra part of this, again, is going to be how we break the number apart or work with it, right, to think about it, and we're going to extend our ideas that we learn here and actually use them for algebraic expressions here soon. So let's try to do this again. I actually want you to try to do this one in your head. Okay, and again, no paper or anything. Try to do it entirely in your head. And it's okay if you don't get it right. I'll share with you the answer in a moment. And we'll talk about some ways that it helps to break this down. Okay, so go ahead and pause now and try to do this one in your head. So let's see actually if you got the right answer. I believe it is 448. In fact, let me check real quick. Remind myself. Yeah. Now, it's okay, again, it's okay if you got that wrong, because my guess is if you try to break it apart or something, it's kind of easy once it gets big enough numbers to lose track of things in your head. I'm going to take a look at this from a new point of view for you, and this is where we come into area of rectangles, because anytime you multiply two things together, it's analogous to finding the area of a rectangle, because remember that the way that we find the area of a rectangle is simply one single multiplication of two numbers. In this case, if we were to say 28 times 16, right? Then whatever the product is of that is representative of that area. Does that make sense to you? But I actually would like to think of this in a slightly different way myself. So I'm going to redraw the same rectangle, more or less, okay? And I'm going to think of the 28 actually as 20 and 8. And let's go ahead and think of the 16 as 10 and 6. And you know what, I almost think of this as like, we have like an office or something, or a room, or a house, whatever, that's split into 4 rooms. And the whole area of the house, if I want to know the whole area of the house, it might be easiest to find the area of the separate rooms first. Like if you're trying to find the square footage of a house, right? You want to know all the floor space and the floor area, but let's say you can't like actually go outside and measure the outside of your walls because there's stuff in the way or whatever. Maybe it's easiest that you do each room individually and then add them together later, all the areas. Okay, so these should have the same area if I do it in different ways, right? And my guess is that you could think about the area of this is simply 28 times 16, and then I should get whatever. But this might make it easier for me, especially with the numbers. So I've kind of chosen to make the numbers something nice in a similar way as we did here. And it actually represents a kind of distribution, but it's a lot of distributing that we have to do. So if you watch here, what we get is 20 times 10, 20 times 6, 8 times 10, and 8 times 6. And of course you can do those in the other order, but if we look at the steps involved here, then 20 times 10 plus 8 times 10 plus 20 times 6 plus 8 times 6 gives me all the smaller pieces added together, and that must equal the whole entire thing. Okay? Now I want you to notice there's actually 4 total pieces here that we broke it up into. And we got 200 plus 80 plus 120 plus 48. And when I'm looking at this, I actually notice that 80 and 120 makes 200. And then 200 plus 200 plus 48 gives me 448. Okay? So that method is actually going to turn out to be really helpful for me when I work with algebraic expressions. And actually, I want you to notice something here with this guy if we'll work the other way. 28 times 16 is, if we think of the 20 as 20 plus 8, right? So this way is harder because we're not, it's going to be the same as this, but we're not using the actual diagram as a visual. But I do want you to make sure that you are able to understand as I go through this, because it'll help you understand better the algebraic part of it, okay? So if you notice here, we can actually do some distribution. We can take this 20 and multiply by all that stuff, and then this 8 can multiply by all that stuff. Don't worry right now that that's 10 plus 6. You can just think of it as 16 still. But what this becomes is 20 times 10 plus 6, right? I distributed the 10 plus 6 in there and in there. And then plus 8 times 10 plus 6, if that makes sense. And then what that's going to do for us is that's going to actually give me 20 times 10 plus 20 times 6 plus 8 times 10 plus 8 times 6. And you can notice that that ends up being the exact same calculation that we had here, okay? So without actually physically drawing in the way it's broken down, we can actually do the distribution. Again, we're using the distributive property, but it's like an extended distributive property. In the end, there's one really interesting way to think about this that works with extended distribution, okay? And this, I'm going to introduce to you, I'm going to use this phrase. When we multiply 2 algebraic expressions together, each with each, what that means is each piece has to end up being matched up with each piece, because look at this. This 20 ended up matched with the 10 and the 6. 20 and 10, 20 and 6. And then this 8 ended up matching with both the 10 and the 6. 8 times 10, 8 times 6. So each piece of this one ended up being multiplied by each piece of this one. That's where we come up with this each with each, okay? So that is a numerical example, okay, just using numbers. And it turns out that this way of writing a diagram and thinking about it like area is really helpful to understand how to multiply algebraic expressions. So the rest of our examples today will just be doing a bunch of examples, and I'll introduce you to using a diagram like this to help us organize. Okay, so to conclude what we just talked about, to multiply algebraic expressions, we're going to learn about a tool called an expansion box, which is pretty much a rectangle that we can think of like finding the area of the pieces. Okay, and it's a really helpful tool to organize using this each with each property I told you about. We're going to start with some simpler examples with just distribution, and I'll show you the basic way to use an expansion box to do a basic distribution, and then we'll get to a couple that have a more complicated distribution, okay? And again, my guess is a lot of you probably are fairly comfortable with multiplying these expressions together. I want to remind you guys, if we have something just written next to each other, algebraic expressions, we intend to be multiplying, even though I didn't write a little dot or a multiplication symbol there. Whereas we don't really do that with numbers, because if I put if I wanted 3 times 8 and I put 3 and 8 together, it looks just like 38, right? Okay, but we do that here with algebraic expressions. So again, you're probably very familiar with, or a lot of you are probably familiar with the fact that I could just, like I did before, distribute. Sometimes we use these little arrows or whatever to show, to distribute this one. Don't forget, this is one term, right? 2x is a product, and that counts as one term. So this only has one thing, and that has two things. So when I say each with each, there's only one thing to go with each of those things, right? So you may already be okay with knowing that this is 2x times x plus 2x times negative 3, which gives me 2x squared. And then 2 times negative 3, these can be multiplied to give me negative 6x, so 2x squared minus 6x. Well, this new tool I told you about, it's helpful to get used to using it. And an expansion box, and you don't need to make the pieces bigger or smaller now, because we have variables, so it's like, we can't accurately say what's bigger than what. So for now, I know that I'm going to be multiplying 2x, which only has one term, so there's only one row. There's not 2 rows, but there's 2 columns, because this has 2 terms. It has an x, and then it has minus 3. And if I think of it like the area, well, this is what's cool about this, like we did in the last one, is 2x times x, the area of that piece is 2x squared, and 2x times negative 3 is negative 6x. And then if I add all the boxes together, you see, then what we get is 2x squared minus 6x, okay? So that's actually going to be my final answer, okay? So why don't you go ahead yourself and pause the video now and do these other two, and then we'll do them together, okay? So let's find the answers for these. And I'm just going to use the expansion box. It's okay with me if you're comfortable without the expansion box for these kinds of ones, but I will want you to use them for the other ones that we do. All these are going to be the same setup here, because they're all one thing and times 2 things, right? Oh, and one thing that sometimes students ask about is, does it matter how I set it up, right? You can see that this one would be 8m squared and 2m plus 5, or we can do the 8m squared and the 2m plus 5 like this. And honestly, it actually doesn't really matter that much, because you and I both know that we can swap the order of multiplication and we still get the same thing, right? 3 times 5 equals 5 times 3. This is kind of saying the same as that. So let's go ahead and do it. This is going to be 16m cubed, because m squared times m gives me m cubed. And then 5 times 8 is 40, and then there's no m's here, so we just have this m squared that stays. And the same thing with what happened here is 16m cubed, and then 40m squared. So no matter what, our final answer here is 16m cubed plus 40m squared. Same thing with this. I'll just do it in this orientation, negative 3p to the 5th. I guess let's keep my color coding correct here, consistent. Negatives are still okay, like we saw there. This still just is an organizational tool, and since we're not talking about literal area, it's okay to negative, because negative area doesn't make sense if we're really thinking area, but negative 15p to the 8th is that one, and then negative 3p to the 5th times p is negative 30p to the 6th. So negative 15p to the 8th minus 30p to the 6th. Okay? Now let's go ahead and look at 3 more examples, but they're going to be a little bit more complicated, kind of like that number one that I did before these. Let's go ahead and get to some more algebraic expressions, and I want you to think about what we're multiplying here. All of these have something in common, okay? Before we had one term multiplied by 2 terms, okay? Remember, a term is each piece. And so in the end, we had just 2 terms because you had to match this one with those 2. So there's 1, 2 matching. So in the end, we had that many terms. Well, here, if we're going to use this with each property, here's 2 things, and here's 2 things, and each of those needs to match with each of those, right? So we've actually talked about the multiplication property recently, about like counting how many things there are. And you've probably heard an example like this before. If I have 2 pairs of pants and 2 shirts, okay, how many outfits do I actually have? Well, I can wear each pair of pants with 2 shirts. So actually there's 4 outfits. In the end, we can just think, oh, there's 2 pants, 2 shirts, 2 times 2 is 4. And the same thing happens here. It's almost like there's 2 terms are like our 2 pants, and these 2 terms are like our 2 shirts. And that means, and we can think about it really easily. This x, right, can distribute in, or I guess I could say this x plus 12 can like go into this x. So this x with that x, and that x with that 12. But then this 3 with that x, and this 3 with that 12. And that gives me 4 total things. So I'll use the expansion box in a minute, but I want you to notice that we could actually distribute this x plus 12 to each of those 2 pieces and get x times x plus 12 plus 3 times x plus 12. Okay, and what this gives me is x times x is x squared, because now we're going to do 2 distributions, plus x times 12 is 12x, plus 3 times x, which is 3x, plus 3 times 12, which is 36. I don't know why it took me a little while to remember that. Okay, and you'll see we have our 1, 2, 3, 4 terms that are the pairs or the matches for all the possibilities in our original problem. Now, you might notice something here is that these 2 terms in the middle actually are what we call like terms, and these are able to actually squish together into one single term, right? Okay. Sometimes we say like, you know, these can't be added. Well, technically x squared plus 12x is being added. It can be added. It can't be written as one term though. So in the end, if you simplify this, you get x squared plus 12x plus 3x is 15x plus 36, and that would be our final result for this one, okay? And to use the expansion box, this is where expansion boxes are really helpful. Well, because we have 2 terms and 2 terms, this actually ends up needing 2 rows and 2 columns. And so I can do my x plus 3 and my x plus 12 here, and watch, we're going to get the same things as I got here. We're going to get x times x is x squared, x times 12 is 12x, x times 3 is 3x, and then 3 times 12 is 36. And in the end, you can see that this is like, oh, okay, well, the area of the whole thing is this plus this plus this plus this. Well, guess what? X squared plus 12x plus 3x plus 36. And something really cool about expansion boxes, especially later when we get to more advanced ones, is if you multiply, the terms that are like terms actually always end up being lined up with each other on diagonals like this. So that 12x and 3x, we can kind of just imagine in our heads, oh, 12x plus 3x is 15x. So we could just directly from here write the answer, the product is x squared plus 15x plus 36. So why don't you go ahead and please do the last 2 examples yourself, and I want you to actually do them this way and this way, okay? Because being fluent in both of those is actually very important. Okay, so pause right now, please, and do them yourself. Let's look at these solutions together. I'm going to do them a little bit quickly. We're going to do x times x plus 7, right? That x plus 7 with that, and that with that. Minus 5 times x plus 7. then I get x squared plus 7x minus 5x plus, oops, not plus, negative 5 times 7 is minus 35. And so I get x squared plus 2x minus 35. And then expansion box method, x plus 7, x minus 5 gives me x squared, 7x minus 5x minus 35. And again, we can see that this, all the area, if you add up all the pieces, ends up being the same thing. Let's look at the next one. This one's going to be 2x times 3x minus 4 plus 1 times 3x minus 4. And the 1's going to be nice because multiply that by 1, it's just going to stay the same. So you might notice that. I'll just put that at the end. Now let's distribute the 2x to the 3x and get 6x squared, and then 2x times negative 4 is going to be negative 8x. Okay? But then we do have these like terms, so we have 6x squared minus 5x minus 4. Negative 8x plus 3x is important. I guess I could have written up here in our prior knowledge about adding or subtracting integers, especially with negatives and stuff, but that's often going to come up. So there's our solution for that. And again, the expansion box, same thing. 2x plus 1, 3x minus 4, and we get 6x squared minus 8x plus 3x, and then minus 4. And if you add all those pieces up together again, the area, we get that total. Okay, so there is our initial exploration on how to multiply algebraic expressions, and we actually we kind of built from the arithmetic, right, the calculations, to the algebra, which is like the relations between the numbers, and we've connected how these algebraic expressions with variables work alongside in with the same rules as we did with the calculations using distribution. So this whole lesson is really all about distribution, but we've learned more advanced ways of doing it. All right, so happy math, and we'll see you next lesson.